Hi, my name is Berkay, and here I am with a simple spectrogram example. In this example, I want to explain you what is a spectrogram, why do we use it in signal processing, how to use it, and in the end, I will going to show you how to make your own spectrogram if you don't have a signal processing toolbox in MATLAB. In here, I have a chirp signal data and I am going to load it. As you can see, my data has three components and one is signal, other one is sample rate, and last one is time vector. And I am going to plot that signal, but first I want you to show this. In this line, I have calculated the power spectral of my chirp signal. And I am going to plot it with my signal. As you can see up here, this is my chirp signal, and this is the power spectral of it. And if you look carefully enough in this signal, you can say that its frequency is changing. And if you look even closer, you can notice that its frequency is increasing into zero, and after zero, it slowly starts decreasing and ends up with a higher frequency than the beginning of the signal. Now, let's look at power spectrum of my signal, and you can see there is something happening in these frequencies, but it is hard to understand what. And this is where the spectrograms comes in. Spectrograms help us when spectral properties of a signal changes over time. It makes it easier to analyze and visualize that signal. If you have a signal processing toolbox in MATLAB, you can use spectrogram function. You just need to specify your signal, your windowing type, and I don't want an overlap, so this one is a blank, and your sampling rate. Let's see the results. So this is the spectrogram of my chirp signal, and it's a frequency over time plot. So which means I can see clearly that frequency change in time. And as you can see, the frequency of signal starts at 10, after that it's increased to 30 at 0, and after that it slowly decreases. For a better comparison, let's look at this. Now this is my chirp signal, and this is the spectrogram of it. And as you can see, I don't have to look very carefully in this signal anymore, because spectrogram of it shows a very clear version of frequency change over time. Now in this section, I want you to show how to make your own spectrogram if you don't have signal processing toolbox in MATLAB. First, I have specified window length of my method, and I have specified it as half a second. After that, I have specified window onset times, and this is basically show us when a Fourier transform take place. Then I have created a time vector, and this time vector specifies time length of the Fourier transform. And this is my home parameter, and I will come back in here in a minute. And lastly, I have created my power vector and added a bunch of zeros to it. Now let's do this, and now this is where the magic happens, and I am calling it magic, but it is a very simple process. First, I am getting a data chunk of my signal, window offset of this iteration, after that window onset plus window length. And after that, I am applying my home windowing method, and let's do it in here. Let's see what's happening, and this is my data chunk, and this is my hum parameter. As you can see, it starts from 0, and after it goes to 1 and goes to 0 again. And when I am applying my hum's parameter, my data chunks change like this. As you can see, hum windowing takes out the beginning of the signal and ending of the signal, but middle part of the signal relatively stays the same. So why I am using hum windowing? It's because it helps to minimize edge effect caused by the wedges method, and this is why I am using Hans windowing. After that, I am calculating the powers of this chunk, and I am adding that power to specified part of my power matrix. And let's do it, and let's see the results. And this is the spectrogram by using wedges method, and you can see the frequency change over time. For a better comparison, let's look at here. Now this is the spectrogram by using spectrogram function, and this is the wedges method. As you can see, it is almost same, but spectrogram function smooths out data a little bit more. But you can use both of them in your signal processing. And this is it. Thank you for listening to me.